Welcome to new. This time we have a system in equilibrium, and the system is holding up different types of fish. So, the first one is fish A, and then the second one is hanging from the second rod. This is fish B right here. This is the second fish. We're going to call it fish B. And then there's an extended rod right there. We have fish D and E. I have to put the eyes and the direction, but you don't have to do that. It's just optional. So this is fish D. And then the last one is fish C. So A, B, C, D. The rods, we can, this distance here, we're given this distance as being equivalent to 30 centimeters. And then this second distance, I should have had this one a little bit to the right, so it's proportional. This one right here would be proportional. So this whole distance is 30 centimeters, and then this one is 7.5 centimeters. This one also we need some adjustment, so we just make sure that it makes more sense in terms of location of these rods. So this one extends all the way up until right there, so we can have a proportional variance in the lengths that we're dealing with. So this one is giving us 15 centimeters, and then this one is giving us 5 centimeters. Also, this one is 5 centimeters, and that's this distance up until there. This distance from D up until that rod is 17.5. I need to adjust that, 17.5 centimeters. Okay, that's the information we're given in this problem. The other piece of information we're given is that the mass of B is equivalent to 0.748 kilograms. That's the mass of B. So the goal of this problem, so this is the information we're given, and then we want to find the mass of A. The mass of B we're given, so we also need to find the mass of C and the mass of D. The system is in equilibrium, so we're going to use that to our advantage to determine the masses. The other thing is that the bars are massless, so they don't have any mass. I mean, you could say they're weightless, because if you don't have mass, then you also don't have any weights going on. So we're going to use torque. Remember, torque is defined as the perpendicular distance times the force itself. The system is in equilibrium, so that means the sum of torques about any points is 0, and also the sum of forces is equivalent to 0. It's a hanging system with all those units that were given. We can change the dimensions to meters if you want to. If you wanted to change it to meters, you'd have to do a unit conversion. So that's 1 meter over 100 centimeter, for example. So that would end up being 0.075 meters. But you know, we don't have to change the the units because they're going to cancel out anyways. The other thing which will strengthen our problem is that we do have we're going to label these ones. So this one, we're going to label it as I. This rod is I. So the force that's pulling up there, we're going to call that F sub I. And then we're also going to label this one 2, Roman 1 and Roman 2. So this force right here will be Roman sub Roman 2. So sub Roman 1 and sub Roman 2, those are the two forces. Also, you know, we have another force that we haven't really talked about, and that's the force at the top. Okay, that's the force at the top. So this whole thing, it's hanging. This one is hanging right here. This one is hanging. I mean, if you wanted to, you could call this F. This one, there's a force there. You know, we can call that 3, the third one, the last one. So this would be F sub 3. It's a system in equilibrium. The fish are hanging from different positions. This is A, this is B, this is C, and this is D. Those are the positions of the fish. The system is in equilibrium, so it's not moving. And we're supposed to find the 3 masses. So we need to find MA, MC, and MD because we're given B. That's the information we're given. So we'll start by looking at 1. We'll start by looking at actually we can rename these subscripts, I think, because we're going backwards. So yes, so these subscripts, instead of calling this one 2, we're going to call this one 1. Yeah, that makes sense. And then we'll call this one 2. So this one is 2. That makes sense. So then the net torque around 1 is going to be 0. The net torque around 1 is 0. And so in the next page, we want to see how we're going to use this. So if you think about the way 1 appears, we have D right there, and then this is 17.50 centimeters. And then we have F1 holding it. I think we have to have a clear diagram on this. So this is super horizontal, so we have to account for that. So this is horizontal all the way like that. And we're only thinking about this section right here, so the initial section. So then this one, is our 1, and the force responsible at that point is F1. That's the force responsible. This distance, as you can recall, is 17.50 centimeters, and this other distance right here is 5 centimeters, even though it's not very proportional, but that's how it is. This is D and this is C, so we're going to start with that, and we're seeing that the net torque around 1 is 0, a Roman 1, remember. So MD MD is going counterclockwise, so it's positive torque, and this one is going clockwise, so it's negative torque. So MDG times 17.5 centimeters minus, because this is a negative torque, MCG times 5.0 centimeters. That's equivalent to 0. And so we can solve for MC, the mass of C. We can solve for the mass of C. So MCG, 5.0 centimeters, becomes equivalent to MDG, 17.5 centimeters. These two G's cancel out. So MC equals to MD, 17.5 centimeters, all of 5 centimeters. Okay, we simplify that. So MC becomes equivalent to 3.5 MD, 3.5 MD. And this is a critical equation that we're going to be using, so we need to keep track of that. That's the first part of the problem involving the torque. In the next page, we're thinking about the sum of forces in the y will be 0, and again we're still at there's a force here, Fi. This is B, and this is C. They're pulling down like that, and this one is also pulling down. And we're saying that if the net torque along the y is 0, the net force, not the net torque, the net force, so Fi minus MDG minus MCG equals to 0. So down is negative, up is positive, upwards is positive, downwards is negative. So that means the force that's holding those two positions is going to be a negative, a positive force, and the other ones are going to be negative. And so Fi becomes equal to MDG plus MCG. We can simplify that. Fi becomes MD plus MC times G, and recall from the previous page we already defined MC as 3.5 MD. So MC equals to 3.5 MD, and that means we can change MC to become 3.5 MD. Okay, so just remember that all we're doing is plugging in, and this is G, so Fi becomes 4.5 MD times G, because this is 1, the coefficient of that is of MD, the initial MD is 1, and then the coefficient of the second MD is 3.5. This is the second equation that's going to be helpful in solving the problem. And then we'll still go ahead and in a new page, but prior to that, we have to move on to the next level. This was level 1. At level 1, we were able to get force 1. Now we are at level 2. We're looking at the impact of force 2. So at level 2, the diagram changes a little bit. At level 2, you have this force is playing a role, so it's pushing downwards. This is F1. Remember, we have D and C hanging from right here. So this is D and C. So this force right here is F1. And then if you go back, you see that the second one is B. So this mass right here is B. And then, of course, F2 is pointing upwards. F2 is pointing upwards, we can emphasize these two forces and those weights, and we can do the same thing on this one. These are the weights we're dealing with, D and C, and they're being supported by Fi. So coming back to this again, we're seeing that the net torque around the second level is 0. This force is counterclockwise, so it's positive. This one is clockwise, so it's negative. So that means that at level 2, we're saying F2, or rather not F2, but F1 times, we have to include the distances 15 and 5. So this distance right here is 15 centimeters. And then this distance right here is 5 centimeters. We'll always try to make them as proportional as possible. So you have Fi times 15 centimeters minus mbg times 5 centimeters equals to 0. This one is negative because it's it's clockwise. And our goal is to get Fi, so we're seeing that Fi 15 centimeters equals to mbg 5 centimeters. So Fi becomes mbg 5 centimeters over 15 centimeters, like that. But then if you can recall, we do have MB from the initial position was given as, from the initial slide was given as 0.748. So this is 0.748 kilograms. That's our MB. And it gives us a chance to plug in the specific numbers that are helpful to solving this problem. So so we need to simplify that. So Fi becomes 0.748 kilograms times G, which is 9.81 meters per second squared, and then times 5 centimeters over 15 centimeters. And so we're just using that formula. And so Fi, now we do have a number for Fi, and it turns out to be 2.44 newtons. 2.44 newtons. That's F sub I, or F sub Roman numeral 1, 2.44 newtons. Again, we're still not there yet. We didn't have the masses yet. We only have the mass of B. We don't have the mass of C or D, but we do need to get F sub I to solve those masses. So going back, going on to the next slide, now we do know that F sub I is 2.44 newtons. If we go back to the initial slide, or the second slide, so to speak, or the third slide, we see there's a relationship. Fi was given as 4.5 mdg. Fi is 4.5 mdg. So that's going to be helpful. Fi is 4.5 mdg. Okay? That's in slide number 3, you can see. And yet Fi, we just found out from the second level using torque of summing up equilibrium torque to 0, we just found out that Fi is 2.44. So we need to plug in that 2.44 newtons. That way we're able to solve for MD. So MD becomes equivalent to 2.44 newtons over 4.5. times G, which is 9.8 meters per second squared. 2.44, 4.5 times G, which is 9.8. And so our MD becomes equivalent to 0.055 kilograms. So now we have the mass of D. And recall, if you go back into slide number 2, MC is defined in terms of MD. So MC is 3.5 MD. So we need to go to a new page, and we'll see that if MC is 3.5 MD, and yet in the previous slide, MD is given as 0.055 kilograms. So it means MC will be 3.5 times 0.055 kilograms. Very helpful. And so we're able to solve MC as 0.19 kilograms. That's MC. So at the beginning, we wanted to find D, we wanted to find C, and we wanted to find A. We were given B. We've solved for, D and C. We've solved for D and C. And now we're only left to solve for A. A happens to be supported by level 3. So in solving this problem, we're going to make sure that we have diagrams showing A being supported at that level. But before, so we have MC, and then we also have MD, and so we don't have F2 yet, but we need to solve for F2. So we have, if you go back on slide number 4, you see where F2 is. So we need to solve for that. So then we're saying this is F2. This is F1. F1 happened to be 2.44 newtons. We don't have to show B and C, but we can highlight D and C right there. And then B was right here. We're given B, MB, as being equivalent to 0.748 kilograms. So our target is to get F2. We're going to use equilibrium for forces. Remember, the net force around level 2 is 0. And so Fii going upwards is positive, going downwards is negative, minus 2.44 newtons, minus MBG equals to 0. Or you can use the variables to emphasize the relationship. So minus F1 minus MBG equals to 0. So to get F2, we need to take F1 plus MBG. F1 was 2.44 newtons plus MB. MBG is the mass of B, or the weight of B, 7.48 kilograms times 9.8 meters per second squared. And so now we have F2, or F subscript Roman 2. And F subscript Roman 2 becomes equivalent to 9.77 newtons. This is going to be helpful in solving the last portion of the problem, because if we get this one, F2, and we have if we get F2, we can combine it with F3, and A and solve that problem. So we're going to make a new page. This is a new page. Now we have F2. So again, this is F2. This is we have to simplify this. So we have, this is F3, the topmost one, the topmost bar, and it's supporting A, and then it's also supporting F2. Remember, this is B, and this is F1, and F1 is supporting D, and F1 is also supporting C. So that's the way we have it. This time we're going to take a torque, sum of torques around this point right here. So the sum of torques around 2 is 0. A has a counterclockwise torques around this position of the first bar, so it's going to be positive torque. B, or rather F2, has a negative torque because it's clockwise. So then what happens is we have sum of, we'll start with the torque, the torque for A. We'll start with the torque for A. So MAG times these two distances. If you go back, you see we have 30 centimeters and 7.5 centimeters. So this is 30 centimeters and this one is 7.5 centimeters. We're going to use that. So MAG times 30 centimeters. That's the torque due to A, minus F2 times 7.5 centimeters. Those two will give you 0. And so to solve for MA, we end up having the force pointing upwards, this force right here, not that force, sorry, but this other force, this one right here, that force, the force producing a torque that way. So we have F sub Roman 2 times 7.5 centimeters all over 30 centimeters times G. This becomes 9.77 newtons because F subscript 2 was 9.77 newtons. We used the sum of forces in equilibrium along the, well, this should have been along the Y. So the sum of forces in equilibrium along the Y should have been 0, and then we're able to get this force right here. That's the number we're using now, 9.77 times 7.5 centimeters, all over 30 centimeters, and then times 9.8 meters per second squared. So when you solve that, you get that the mass of A happens to be 0.25 kilograms. 0.25 kilograms. So this is a problem that's very process based. We simplified it by focusing on specific sections. So this was level 1, as you can recall, and then we went on to level 2, and then finally we went on to level 3. And at each level, we computed the force holding up. This was F subscript 1 and F subscript 2. We used equilibrium for torque, and we also used the equilibrium for forces. So initially, we computed the mass of C based on torque around this level, and then we went on to compute the force that's holding D and C using the equilibrium of force, and that was F subscript 1. It was relative to MD, and we did that by doing a substitution of MC into this equation, and then we're able to compute the exact value of the force holding D and C as 2.44 newtons. We went ahead and using that force, we were able to plug in based on the fact that that force, F subscript 1, was equivalent to 4.5 mdg. And using that relationship, we plugged in 2.44 newtons, and were able to solve for the mass of D, which happens to be 0.055 kilograms. Remember, we're given the mass of B as 0.748 kilograms. And so the next thing, since now we know the mass of D from this previous slide, we can use the equation that we picked up at the beginning for mass of C to solve for the mass of C. So we plug in 0.055 as the mass of D, and we're able to solve for the mass of C. And then finally, using the sum of forces in the y direction, we're able to determine the force holding Fi and the mass of B together, and that force is equivalent to 9.77 newtons. And using torque, we're able to simplify for the mass of A as 0.25 kilograms. So hope you enjoyed the problem. Feel free to send any questions or comments, and have a wonderful day. Okay, thanks. Bye.